Welcome to Spring LIB.
For this problem, we have been given a listing of 8 different sequences. And for each sequence, we need to find the first 10 terms. So in all these cases, we will probably be given a starting point and a definition, some way of getting from one to the next. So we'll just take each one in turn, and we'll kind of make a grid of all 10 numbers and for each one individually, and see what we get. Okay, so the first one. Our sequence is obtained by starting with 10. So 10 is our first term. Each term after that we get by subtracting 3 from the previous term. So we just need to subtract 3. 10 minus 3 is 7. 7 minus 3 is 4. 4 minus 3 is 1. Then negative 2, negative 5, negative 8, negative 11, negative 14, negative 17. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, that's 10. So those are the first 10 terms of that sequence. And it could go on forever because we can always keep subtracting 3. But we just need to find the first 10. Okay, how about B? The sequence whose nth term is the sum of the first n positive integers. Well, the first one's easy. I'm just adding 1. Okay, the second one, I'm going to add 1 and 2. For the third one, 1 plus 2 plus 3. Fourth term, 1 plus 2 plus 3 plus 4. So we're taking that last term and adding n to it. If I want to add 1 plus 2 plus 3 plus 4, gives me 10, plus 5 is 15, plus 6, plus 7, plus 8, plus 9, plus 10. Okay, sequence C. The sequence whose nth term is 3 to the n minus 2 to the n. Well, we're going to do the first few of these. I'll just talk through. After we get to about n equaling 4 or 5, you're going to need to get your calculator out. These numbers will get very large. But let's start with n equaling 1. If n is 1, then this is 3 minus 2, or 1. If n is 2, we have 9 minus 4, or 5. If n is 3, 27 minus 8, which is 19. If n is 4, that's 81 minus 16, or 65. And again, from here, I recommend using a calculator to calculate the rest of these. You'll end up with 211, 665, 2,059, 6,305, 19,171, and for 10, that's 3 to the 10th minus 2 to the 10th is 58,025. Okay. Let's look at sequence D. The sequence whose nth term is, I'm just going to write this so we can see it, it's the floor function of the square root of n. Now, if n is a perfect square, this is easy because that gives us an integer. So if n is 1, it's 1. If n is 4, the value of this is going to be 2. And if n is 9, the value is 3. But what about the ones in between? Well, it's a floor function. So whatever the value is, we're going to bring it down to the next lowest integer. So everywhere where the value is between 1 and 2, the floor function is going to let it go to 1. Everywhere where the value of that square root is between 2 and 3, the floor function brings it down to 2. And then that last one will be 3 because it'll be 3 point something. The floor function brings it back down to 3. Okay, let's go on to E. E says the sequence whose first 2 terms are 1 and 5. So we'll put those down. And each succeeding term is the sum of the 2 previous. So we just have to do adding for this one. 1 plus 5 is 6. 5 plus 6 is 11. 6 plus 11 is 17. 11 plus 17 is 28. Then we get 45, 73, 118, and 191. Okay, just give ourselves a little more space here. And look at sequence F. The sequence whose nth term is the largest integer whose binary expansion has n bits. Okay, if you haven't done much with binary numbers, I recommend taking a moment and just looking at section 4.2. It talks about what binary numbers are. They're numbers that only use zeros and ones to represent things. So let's take a look, and I'm just going to, I'm going to be erasing this in a little bit probably, so I'm just going to write this in red below. If I have a binary number with one digit, the biggest number it can be is 1. Okay. What about a binary number with 2 digits? Well, that's going to be 3 in binary. The biggest one with 3 digits. Well, this means I have 2 ones. That does not mean that. It means I have 1 1, I have 1 2, and I have 1 4. So that's going to give me a value of 7. What if I have 4 digits? Well, that means I'll have the 1 and 2 and 4, plus I'll have an 8. Remember, in our normal base 10, every succeeding position, place value, is 10 times bigger. Okay, it's 10 to the first, 10 to the second, 10 to the third. In binary, these are powers of 2. So 2 to the 0, 2 to the first, 2 to the second, 2 to the third. That's our 8 there. So for that number 4, I'll have an 8 plus 4 plus 2 plus 1, and that's going to be 15. If I have 5 digits, that means I'm adding 1 in the 16s column. So that means I have 31. 6 digits means I'll have 6 ones. That's 1 in the 32nd spot, which means I have 63. Okay. The next time I add a digit, it's going to be in the 64 column. So I'm going to add 64. That gives me 127. For my next digit, that's another power of 2. That's 255. The next one I add is another power of 2. That's 511. And my very last one is 1023. Okay, 2 more sequences to go. G. The sequence whose terms are constructed as follows. We start with a 1. Then we're going to alternate adding and multiplying. We're going to do 1s, 2s, 3s, and so on. So add, then multiply. So add 1, multiply by 1. Add 2, multiply by 2. Add 3, multiply by 3. Add 4, multiply by 4. And we'll finish by adding 5. So that's our sequence for the first 10. Again, we could go further on all of these. We just are charged with finding the first 10 digits or the first 10 terms. Okay, and the last one. The sequence whose nth term is the largest integer k such that k factorial is less than or equal to n. Okay, so if n is 1, well, k would be 1. K factorial, 1 factorial is going to be 1. What's our next one? 2 factorial is 2. So that's going to go there. Well, what is 3 factorial? 3 factorial is 6. So I'm going to have 1, 2, 3, 4, 5, 6. When I have my 6th term, that's going to be 3. But I want to have everything, k factorial needs to be less than or equal to n. So everything between here has to stay 2. I can't jump up to 3 till I hit that 6th position. Okay. Then 4 factorial is 24. So if I kept going, I would have to go out to the 24th term before I would change my k to change my value to 4. Until then, I need to stay at 3 because that is the that's the k where k factorial is going to be less than or equal to my term. So those are my sequences A all the way through H.